My project is about parallel universes. We'll start off with some background information. The multiverse theory was proposed by a Princeton student and physicist in 1954 by the name of Hugh Everett III. Now, to understand his theory, you must understand quantum physics. You have to think really, really small, smaller than an atom. Electrons which circle the nucleus of an atom are swirling around in multiple states at the same time. They're hard to pin down. It's only when we measure the position of an electron that we force it to have a specific location. So basically, quantum physics is understanding and finding the location of really small particles like electrons and stuff. With regular sized objects, we can calculate the relativity or location with 3 dimensions of space plus the dimension of time. But whenever you find the point of where an electron is located, it's much more difficult because they travel in wave functions. And in order to know a particle's position, you must calculate an infinite amount of dimensions or points throughout time and space. This basically sounds impossible, but it's not. According to Schrodinger's rule, wave functions move smoothly at a constant momentum. Because everything is the same, the position of a particle is uncertain. So it is believed the particle is everywhere in the wave function all at once. But then the Born rule comes into play when the wave function's momentum is inconsistent. The waves taller than the rest give us a clue to where the particle is located, but now we rely on probability between these points. Which one is most likely to carry the particle? I found this really cool 3D informational graphic that actually kind of explains more of what I just showed you, which is called a superposition. It's whenever you have a combination of 2 or more waves inside of a wave function that have different frequencies and different momentums. Here we have a wave function with 2 possible locations where a particle could be located in the superposition. A weird thing happens though whenever one tries to measure or observe a wave function. The wave function collapses, making everywhere else 0 except for the particle is located. So the wave function narrowed it down and found our particle, which is great. But a minute ago, Schrodinger said the particle was everywhere at once in the wave function. And what happened to the other possible waves and their probabilities? Hugh said, let's say you take a cat and you put it in a box, and this cat is like a limbo state. Otherwise meaning the cat is in a superposition, both dead and alive. Schrodinger said one of 2 things would happen. Either whenever you open the box, the cat would be dead, or whenever you open the box, the cat would be alive. You can't have both. But Hugh argued if they were both dead and alive inside the box, then that means that they're both dead and alive outside the box. So whenever you open the box, an entanglement happens where everything splits. So the cat splits, the box splits, and you split. And so there's 2 different copies. But the thing is that only one copy can see a dead cat, and then another copy can see a cat that's alive. And so that's why you have these 2 different probabilities, because you can only see one. But in reality, it's still a superposition. And there's still another reality out there.